Section 2.3 continues our work with limits and with continuity. Continuity at a point. Any function, y equals f of x, whose graph can be sketched in one continuous motion without lifting the pencil, is an example of a continuous function. So, find the points at which the given function is continuous and the points at which it is discontinuous. So if I were drawing this function, and I started here at 0, I could go I'll stop. I could go from 0 up to here, then I would have to lift my pencil, and then I could come down here. So, continuous. It is continuous at 0. I put my pencil down there, I do not have to lift it up to draw a function. It's continuous at 6. Again, I go all the way to 6. So the end points are points of continuity. Now, from 0 to 6, any point between 0 and 6, and we call some given x value c, but not between 2 and 3. So in other words, it is continuous from 0 to 2 and from 3, whoops, there should have been a C in there. Continuous from 0 to 2, and 2 is not included. I'm not sure, oh, yeah, because not there. And then from 3, which is included, to 6. Okay, so our sections of continuity are those places that we can draw without lifting up a pencil. Discontinuity. At x equals 2, it is discontinuous. Between 2 and 3, and anything greater than 6. So less than 0, between 2 and 3, and to the right of 6 are also discontinuous. So let's connect this to limits. So the limit as x approaches 0 from the right equals f of 0. The limit as x approaches 6 from the left is f of 6. The limit as x approaches c, in other spots, remember we restricted c, the c could not be between 2 and 3, is also f of c. The limit as x approaches 2 does not exist. These points are not in the domain of f. So at 0, since it's continuous, let me draw this a little better because these connect to each other. At x equals 0, the limit is f of 0. At x equals 6, the limit is f of 6. For these given c values, the limit of f of x is f of c. At 2, it does not exist, and these points are not in the domain. So continuity at a point. Interior. If function y equals f of x is continuous at an interior point c, if the limit as we approach c equals f of c. Endpoints. A function is continuous at a left endpoint or continuous at a right endpoint if, as we approach the left endpoint from the right and the right endpoint from the left, we also can find function values. Write this down. We're going to be doing some examples in class, so I know that the terminology is a little confusing, but we're going to go through it in class time. Okay, if a function f is not continuous at a point c, we say that f is discontinuous, and c is a point of discontinuity. C does not have to be in the domain of f, so any point outside of the domain is by definition discontinuous. Alright, let's look at these graphs. So the first graph is a solid line. It goes from here to here. There are no points of discontinuity, and it's a straight, every point on the function is a point of continuity. This graph has a little hole at 1. Hopefully you can see that. So since there is a hole, f of 0, oh, where'd it go? 0 is a point of discontinuity. This particular point of discontinuity, along with the one here, is called a, oh my gosh, my one just went blank, hold on. Well, I know what I'm saying. So this is an open circle here. We also have an open circle here, but there is a function value there. This is called a removable discontinuity. Down here, we go from here, and then there's this jump. There's no gap in the domain, but there's a jump in the function. This is called a jump discontinuity. Here, there is a break. Both sides are going up. This is an infinite discontinuity. That's happening when we've got a vertical asymptote. And this one, the graph is not great. It oscillates. It goes up, down, up, down, up, down. And it gets squished closer and closer. But this middle part is still going up, down, up, down, up, down. So this is called an oscillating, I hope I spelled that right, oscillating discontinuity. So these are our four main kinds of discontinuities that we're going to be looking at. Removable, where there's a little hole. Jump, where we jump from one value to another. Infinite, where we're going up on both sides or down on both sides of a vertical asymptote. And oscillating, where it keeps going up and down and up and down and up and down, and if we spread it out, it would still keep going up and down and up and down and up and down, and there's no way to say what value is being approached. Continuity at a point. So here's our graph, and we want to look for a point of discontinuity. Well, we know that we're going to have a discontinuity whenever the denominator is 0. So the infinite discontinuity occurs at 1. What we're looking for with discontinuities are breaks in the graph. A function is continuous on an interval if and only if it is continuous at every point of the interval. A continuous function is one that is continuous at every point of its domain. A continuous function need not be continuous on every interval. In other words, I can have a function that is continuous on a particular interval, but not across every interval. So it's continuous here from negative infinity and up to c. We'll call this some value c. So this function has some sections of continuity. Properties, these are just like the ones we've seen before. Jot them down if you'd like. If f and g are continuous at c, then f plus c is also continuous, f plus g is continuous, f minus g, product is good. All of these are still going to be continuous if we do composite functions. And if f is continuous at c and g is continuous, then so is g of f of c. Okay? So, intermediate value theorem. A function y equals f of x that is continuous on a particular interval takes on every value between f of a and f of b. In other words, if y is between f of a and f of b, then y equals f of c for some c. Write that down, then I'm going to show you a picture that'll make a whole lot more sense. So here we have the point a, f of a as one endpoint, and we have the point b, f of b as another endpoint. Any value that I can find between a and b, where'd my pen go? Any value between a and b that we call c has a y value that is between f of a and f of b. So all of the values between f of a and f of b have to be found somewhere between a and b. So that's an intermediate value theorem. It says that if it's continuous from a to b, then at some point in that interval from a to b, all the values from f of a to f of b also occur. So this is why the graph of a function cannot have breaks. It will be connected, a single unbroken curve, and it will not have jumps or branches. That's our definition again of continuous. And that's it.